The National Electrical Code does not explicitly prohibit paralleling secondary conductors of a transformer to feed separate electrical panels. However, it is important to consider several code sections. NEC Article 450.4 states that transformers shall be installed in accordance with the manufacturer's instructions. NEC Article 450.4f says that power transformers shall not be used to supply portable or mobile equipment or assemblies. NEC Article 450.13 indicates that the secondary winding of a transformer exceeding 600 volts nominal shall not be connected to a branch circuit unless the circuit is provided with a proper grounding connection. Several considerations must be kept in mind. Firstly, verify with the transformer manufacturer if they allow paralleling of secondary conductors. Secondly, the requirements for permanent installations may not fully apply because this is a temporary installation. Thirdly, ensure that the paralleled conductors are properly sized and installed to handle the load. Fourthly, the transformer secondary must be properly grounded as required by NEC Article 450.13a. A recommended approach is firstly check with the transformer manufacturer for paralleling restrictions. Secondly, use appropriately sized conductors for the load and circuit protection. Thirdly, use a single conduit or raceway for both paralleled conductors. Fourthly, install a grounding conductor in the conduit. Fifthly, use lugs rated for parallel wiring. Sixthly, provide clear labeling to identify the paralleled conductors. NEC Article 445.12 provides guidance for paralleling conductors. It states that conductors used in parallel shall be the same length and size and connected in parallel only at the point nearest their supply. While this section specifically applies to conductors and raceways, it provides a good general principle to follow for paralleling transformer secondary conductors. Paralleling secondary conductors of a transformer to feed two 100 amps panels is generally acceptable by code, provided the safety and grounding requirements are met. It is recommended to consult with the transformer manufacturer and follow best practices for proper installation and operation. Let's delve deeper into the specific requirements and recommendations for paralleling transformer secondary conductors to feed two 100 amps panels, focusing on the technical aspects and code compliance. Firstly, considering NEC Article 450.4a, the manufacturer's instructions are paramount. These instructions might specify limitations on paralleling, conductor sizes, or other critical parameters. Ignoring these instructions could lead to violations and potentially unsafe conditions. Obtain the transformer's documentation and thoroughly review any stipulations regarding secondary conductor configurations. Secondly, NEC Article 450.4f prohibits using power transformers to supply portable or mobile equipment. Ensure that the temporary construction trailers are not classified as such, as this would invalidate the use of a transformer in this manner. Consult the relevant definitions and classifications within the NEC to confirm compliance. Thirdly, with reference to NEC Article 450.13a, proper grounding is essential. The grounding electrode conductor should be sized according to NEC Table 250.66. and the grounding connections must adhere to NEC Article 250. Ensure the grounding system is robust and effectively bonded to the transformer enclosure and the connected panels. Now let's explore the practical considerations. When paralleling conductors, several factors need careful attention. Firstly, conductor sizing must be adequate to handle the calculated load. Use NEC Article 310.15 and the associated tables to determine the appropriate conductor size based on the ampacity requirements. Account for ambient temperature correction factors and conductor derating factors as necessary. Remember that the conductors must be sized to carry at least 125% of the continuous load as per NEC Article 215.3. Secondly, ensure that the paralleled conductors are of the same length, material, and insulation type. This minimizes impedance imbalances and ensures equal current sharing among the conductors. Unequal current sharing can lead to overheating and premature failure of one or more conductors. Thirdly, the termination points for the parallel conductors must be properly designed and installed. Use lugs specifically listed and labeled for parallel conductor applications. These lugs provide secure and reliable connections, minimizing the risk of loose connections and overheating. Torque the lugs to the manufacturer's specifications using a calibrated torque wrench. Fourthly, the overcurrent protection for the parallel conductors must be carefully coordinated. Each panel should have its own set of overcurrent protection devices sized according to the ampacity of the conductors and the connected load. The main breaker in each panel should not exceed the ampacity of the conductors feeding that panel. It's also advisable to use appropriately sized fuses or circuit breakers in the transformer secondary to protect the transformer itself. Fifthly, consider the raceway fill requirements. When running multiple conductors in a single conduit, ensure that the conduit fill does not exceed the limits specified in NEC Chapter 9 Table 1. This ensures adequate ventilation and prevents overheating of the conductors. Use appropriately sized conduit to accommodate the paralleled conductors and the grounding conductor. Sixthly, labeling is critical for safety and maintenance. Clearly label each conductor at both ends to indicate its function and circuit designation. Use durable, weather-resistant labels that will withstand the harsh conditions of a construction site. Additionally, post a warning sign near the transformer indicating that the secondary conductors are paralleled and that special precautions should be taken when working on the system. Seventhly, inspect the installation thoroughly before energizing the system. Verify that all connections are tight, conductors are properly supported, and grounding connections are secure. Use a multimeter to check for continuity and insulation resistance. Perform a voltage test to confirm that the transformer is operating correctly and that the voltage levels are within acceptable limits. Finally, document the installation meticulously. Keep detailed records of conductor sizes, raceway types, overcurrent protection devices, grounding connections, and test results. This documentation will be invaluable for future maintenance, troubleshooting, and inspections. Now, regarding temporary installations, while the NEC does allow for some flexibility in temporary wiring, safety is still paramount. NEC Article 590 covers the requirements for temporary installations. Ensure that all temporary wiring is protected from physical damage and that all equipment is properly grounded. Conductors should be supported to prevent strain on connections. Use ground fault circuit interrupters for all receptacle outlets used by personnel as required by NEC Article 590.6. Regularly inspect the temporary installation for any signs of damage or deterioration. Replace any damaged or worn components immediately. Remove the temporary wiring as soon as the construction project is complete. In addition to the NEC requirements, consider any local codes or regulations that may apply. Local jurisdictions may have additional requirements for electrical installations, particularly temporary installations. Contact the local electrical inspector to determine if any specific permits or inspections are required. Let's consider a practical example. Suppose the calculated load for each 100 amps panel is 80 amps. This means each set of paralleled conductors must be capable of carrying at least 80 amps * 1.25 equals 100 amps. Referring to NEC Table 310.16, we can see that a 1/0 AWG copper conductor with THHN insulation is rated for 150 amps at 75 degrees Celsius. However, we must also consider any dirting factors. If the ambient temperature is higher than 30 degrees Celsius, we must apply a temperature correction factor. If there are more than 3 current carrying conductors in the raceway, we must apply a conductor dirting factor. Assuming a temperature correction factor of 0.88 and a conductor dirting factor of 0.8, the adjusted ampacity of the 1/0 AWG conductor is 150 amps * 0.88 0.8 equals 105.6 amps. This is sufficient to carry the 100 amps load. Therefore, we can use two 1/0 AWG copper conductors in parallel for each panel. The grounding electrode conductor should be sized according to NEC Table 250.66. For a 75 kVA transformer with a 480 volt primary and a 240 volt secondary, the secondary current is approximately 180 amps. The grounding electrode conductor should be at least a number 6 AWG copper conductor. The equipment grounding conductor should be sized according to NEC Table 250.122. For a 100 amps overcurrent protection device, the equipment grounding conductor should be at least a number 8 AWG copper conductor. Use a 2-inch RNC conduit to accommodate the full 1/0 AWG conductors and the number 6 AWG grounding electrode conductor. Ensure that the conduit fill does not exceed 40% as required by NEC Chapter 9, Table 1. Install a 100 amps main breaker in each panel to protect the conductors and the connected load. Label each conductor at both ends with its circuit designation and function. Post a warning sign near the transformer indicating that the secondary conductors are paralleled. Inspect the installation thoroughly before energizing the system. Verify that all connections are tight, conductors are properly supported, and grounding connections are secure. Use a multimeter to check for continuity and insulation resistance. Perform a voltage test to confirm that the transformer is operating correctly and that the voltage levels are within acceptable limits. Document the installation meticulously. Keep detailed records of conductor sizes, raceway types, overcurrent protection devices, grounding connections, and test results. This documentation will be invaluable for future maintenance, troubleshooting, and inspections. By following these steps, it's possible to safely and effectively parallel transformer secondary conductors to feed T100 amps panels in a temporary construction setting while ensuring compliance with the NEC and other applicable codes and regulations. The importance of consulting with qualified electrical professionals and adhering to all safety precautions cannot be overstated. Now let's clarify on the types of lugs that can be used for terminating parallel conductors. Firstly, understand that not all lugs are created equal. Standard lugs are designed for terminating a single conductor, while parallel conductor lugs are specifically engineered to accommodate multiple conductors simultaneously. Using a standard lug for parallel conductors can result in improper termination, loose connections, overheating, and potentially hazardous conditions. Parallel conductor lugs are typically larger and more robust than standard lugs. They have multiple barrels or openings to accommodate the individual conductors. The barrels are designed to provide a secure and reliable connection for each conductor, ensuring equal current sharing and minimizing the risk of overheating. There are several types of parallel conductor lugs available, each with its own advantages and disadvantages. One common type is the set screw lug. Set screw lugs have one or more set screws that are tightened to secure the conductors in the barrel. These lugs are relatively inexpensive and easy to install, but they may not provide the most reliable connection, especially in high vibration environments. Another type is the compression lug. Compression lugs are installed using a special crimping tool that compresses the lug around the conductors. Compression lugs provide a very secure and reliable connection, but they require a more expensive crimping tool and may be more difficult to install. A third type is the mechanical lug. Mechanical lugs use a bolt or screw to tighten the conductors in the barrel. Mechanical lugs are a good compromise between set screw lugs and compression lugs. They provide a more reliable connection than set screw lugs, but they are less expensive and easier to install than compression lugs. When selecting parallel conductor lugs, it's important to consider the following factors. Firstly, the size and number of conductors. The lug must be sized correctly to accommodate the number and size of conductors being terminated. Refer to the lug manufacturer's specifications to determine the appropriate lug size. Secondly, the conductor material. The lug must be compatible with the conductor material. For example, aluminum lugs should be used with aluminum conductors, and copper lugs should be used with copper conductors. Using dissimilar metals can lead to corrosion and connection failures. Thirdly, the environmental conditions. The lug must be suitable for the environmental conditions in which it will be used. For example, If the lug will be exposed to moisture or corrosive chemicals, it should be made of a corrosion-resistant material. Fourthly, the ampacity rating. The lug must have an ampacity rating equal to or greater than the ampacity of the conductors being terminated. Fifthly, the listing and labeling. The lug should be listed and labeled by a recognized testing laboratory such as Underwriters Laboratories or Canadian Standards Association. This ensures that the lug meets applicable safety standards. When installing parallel conductor lugs, it's important to follow the manufacturer's instructions carefully. Firstly, strip the insulation from the conductors to the correct length. Secondly, clean the conductors thoroughly to remove any dirt or corrosion. Thirdly, insert the conductors into the lug barrels. Fourthly, tighten the set screws or bolts to the manufacturer's specified torque. Fifthly, inspect the connection to ensure that it is secure and that the conductors are properly seated in the lug barrels. Remember, the selection and installation of parallel conductor lugs are critical for the safe and reliable operation of electrical systems. Always consult with qualified electrical professionals and follow all applicable codes and standards. Let's address grounding of the transformer in more detail. Grounding the transformer is absolutely crucial for safety and proper operation. A properly grounded transformer provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protection devices to quickly trip and clear the fault. This minimizes the risk of electrical shock, fire, and equipment damage. The NEC provides detailed requirements for grounding transformers in Article 250. Firstly, the transformer secondary must be grounded if the system voltage is less than 50 volts. Secondly, the transformer secondary must be grounded if the neutral point is used as a circuit conductor. Thirdly, the transformer secondary must be grounded if the system is a three-phase, four-wire system. There are two main types of grounding systems commonly used for transformers. Firstly, the solidly grounded system. In a solidly grounded system, the neutral point of the transformer secondary is directly connected to ground. This provides a very low impedance path for fault current, allowing the overcurrent protection devices to quickly trip. Solidly grounded systems are typically used in industrial and commercial applications where high fault currents are expected. Secondly, the impedance grounded system. In an impedance grounded system, a resistor or reactor is inserted between the neutral point of the transformer secondary and ground. This limits the fault current to a predetermined level, reducing the stress on the electrical system and equipment. Impedance grounded systems are typically used in applications where it is desirable to limit the fault current, such as in hospitals and data centers. The grounding electrode conductor should be sized according to NEC Table 250.66. The size of the grounding electrode conductor depends on the size of the transformer and the type of grounding system. The grounding electrode conductor should be connected to a grounding electrode, such as a ground rod, ground plate, or underground metallic water pipe. The grounding electrode should be located as close as possible to the transformer. The equipment grounding conductor should be sized according to NEC Table 250.122. The size of the equipment grounding conductors depends on the size of the overcurrent protection devices protecting the circuits. The equipment grounding conductors should be connected to all non-current carrying metal parts of the electrical system, such as equipment enclosures, conduit, and junction boxes. All grounding connections must be made using approved methods and materials. Grounding connections should be clean, tight, and corrosion resistant. The grounding system should be inspected regularly to ensure that it is in good condition. Any damaged or corroded grounding connections should be repaired or replaced immediately. Now we will look at the raceway requirements in more depth. The type of raceway used for the transformer secondary conductors must be suitable for the environment in which it will be installed. In this case, the secondary wiring will be installed in rigid metal conduit or RMC. RMC is a durable and robust raceway that provides excellent protection for conductors. RMC is suitable for both indoor and outdoor applications, and it can be used in wet, damp, or corrosive environments. The NEC provides detailed requirements for the installation of RMC in Article 344. Firstly, the RMC must be properly supported. RMC should be supported at intervals not exceeding 10 feet. Secondly, the RMC must be securely connected to boxes and fittings. RMC should be connected to boxes and fittings using threaded couplings and connectors. Thirdly, the RMC must be reamed to remove any sharp edges. RMC should be reamed after cutting to remove any sharp edges that could damage the conductors. Fourthly, the RMC must be installed in a neat and workmanlike manner. RMC should be installed in a neat and workmanlike manner, and it should be free from any kinks or bends that could restrict the flow of current. The size of the RMC must be sufficient to accommodate the conductors being installed. The NEC provides detailed requirements for conduit fill in Chapter 9, Table 1. The conduit fill is the percentage of the conduit cross-sectional area that is occupied by the conductors. The maximum allowable conduit fill depends on the number of conductors in the conduit and the type of conduit. For RMC, the maximum allowable conduit fill is 40% for 3 or more conductors. The conductors must be installed in the RMC in such a way that they are not damaged. The conductors should be pulled through the conduit using a pulling lubricant. The conductors should not be twisted or kinked. The conductors should be properly supported within the conduit to prevent strain on the connection. Now, regarding overcurrent protection, the overcurrent protection devices for the transformer secondary conductors must be sized to protect the conductors and the connected equipment. The NEC provides detailed requirements for overcurrent protection in Article 240. Firstly, the overcurrent protection devices must be sized to protect the conductors from overloads and short circuits. Secondly, the overcurrent protection devices must be sized to protect the connected equipment from damage. Thirdly, the overcurrent protection devices must be readily accessible. Fourthly, the overcurrent protection devices must be properly labeled. The overcurrent protection devices for the transformer secondary conductors should be located as close as possible to the transformer. This minimizes the length of unprotected conductors. The overcurrent protection devices for the transformer secondary conductors should be sized according to the ampacity of the conductors. The ampacity of the conductors is determined by NEC Table 310.16. The overcurrent protection devices should be rated to interrupt the available fault current at the point of installation. The available fault current is the maximum amount of current that could flow during a short circuit. The available fault current can be calculated using a fault current calculator. The overcurrent protection devices should be properly coordinated to ensure that the overcurrent protection device closest to the fault will trip first. This minimizes the extent of the outage. The overcurrent protection devices should be regularly inspected to ensure that they are in good condition. Any damaged or defective overcurrent protection devices should be replaced immediately. To summarize, paralleling transformer secondary conductors to feed two 100 amps panels is a common practice, but it requires careful consideration of the NEC and other applicable codes and standards. By following the guidelines and recommendations outlined in this information, you can ensure that the installation is safe, reliable, and code compliant. Always consult with qualified electrical professionals and follow all safety precautions. Remember, electrical work can be dangerous, and it should only be performed by qualified individuals.